Hi everybody, this is Cal again. We're going to split this reading into two videos. The first one will cover section 1.3, the second one will cover sections 2.1 and 2.2. So let's cover section 1.3 here. Section 1.3 is about finite and infinite sets, and really what the section is about the size of sets. There's a basic tool that we use here to talk about the size of sets, and that tool is the following. And you make sure that you understand what I'm about to say here. If there is a bijection between two sets, then those sets have the same size. They have the same number of elements. And make sure that you go back to section 1.1 and look at the definition of a bijection and understand why that should be true, why two sets with a bijection between them should have the same number of elements. I think this makes a lot of sense when you're dealing with finite sets, and not as much sense when you're dealing with infinite sets. But I think the basic notion should kind of make sense to you. With that in mind, let's kind of go through the section here. Definition 1.3.1 lays out some ground rules for the size of sets, what it means for a set to have 0 elements, n elements, finite, infinite. And I urge you to pay special attention to Part B of this definition. A set S has n elements if there's a bijection from the set of the first n natural numbers. So think of an object lesson here. Think of a set with size 5, maybe the set A, B, C, D, E, right? There is a bijection from the set of the first 5 natural numbers, 1, 2, 3, 4, 5, onto A, B, C, D, E. And what you can kind of think of for this bijection is think of it as an enumerated list of the elements in your set A, B, C, D, E. Think about how that would look. You would write down 1, A, 2, B, 3, C, 4, D, 5, E, and that's a correspondence, right? That's a bijection. Being able to list, to enumerate the elements in your set this way, it gives you a bijection between the two, establishes that they are the same size. Which is all well and good for finite sets where the notion is kind of obvious. But for infinite sets, this is still going to be true. And we'll say a few things about that going forward. Now, 1.3.2 is a uniqueness theorem about the size of sets. 1.3.3 says that n, the natural numbers, is infinite. Make sure you understand what those are saying. Theorem 1.3.4 gives you a few basic tools for dealing with the sizes of sets. Make sure you understand what those are saying. The book gives you a proof of Part A, and it recommends that you prove Part B and C, and I absolutely recommend that you prove Parts B and C. I think those are really good examples of things that you could deal with from this section. Theorem 1.3.5 also gives you a couple of rules about the sizes of subsets. It says that if you have a subset of a finite set, it's also finite. If you have an infinite set inside another set, the bigger set is infinite, and that should make sense. Make sure that you read and understand the proofs of this theorem. Now we get into the idea of countable sets, starting at the bottom of page 17. This terminology is very basic and stuff that you should absolutely know. And make sure you understand how this works with the idea of bijections at the bottom of 17, top of 18. 1.3.7 gives some examples of countable sets, sets that have, countably infinite sets rather, sets that have the same size as the natural numbers. And this is a little bit weird here. This says things like the set of even numbers has the same size as the natural numbers. You kind of think to yourself that that doesn't make sense because there's half as many even numbers. But at the same time, there is a bijection from the natural numbers to the even numbers. Similarly, the set of all integers has the same size as the natural numbers. And part C is important as well. Theorem 1.3.8 blows your mind even more. The set of ordered pairs, n cross n, has the same size as just the set n itself. That's really weird. And make sure that you read, at the very least, the informal proof and the pictures in the bit below. The formal details of this proof are maybe not so important. It's not that important to me that we actually be able to explicitly state a bijection between these two sets, which is what the book is doing here. That being said, I mean, read through it once, try to understand what it's doing. It's not as complicated as it looks, just the notation's a little bit wonky. And since this sort of construction is a pain in the butt, theorems 139 and 1310 give you a couple of tools to kind of avoid these wonky bits. Theorem 1310 in particular is really important. 139 is basically an infinite analog of 135. But 1310 is really important, and you should understand why that should work, so make sure you read the proof pretty carefully. Now 1311 might kind of blow your mind a little bit again. The set of rational numbers, all fractions of integers, is the same size as just the set of natural numbers, which seems like it ought to be a lot smaller. But these really do have the same size. Make sure you read this proof. It follows from the previous proof. I mean, that's a really cool result. And 1312 is a really cool result too. A countable union of countable sets is countable. We'll tie up this section with 1313, Cantor's theorem, which kind of gives us an opposite view. We've just been showing that a lot of sets are the same size as the natural numbers. Cantor's theorem says that there are sets that are much bigger. In particular, it doesn't say it right here, but one of these sets that is much bigger than the natural numbers, where there is no bijection between the naturals and the set, is the real numbers. Real numbers are bigger than the naturals, than the rationals, than all those. There is no bijection between the naturals and the reals. And we'll get into that in the next chapter, but this Cantor's theorem is the basic technique that we will use. And the proof is really, really cool, so read the proof. The blurb about Cantor is cool, too. I mean, I'm not going to test you on it or anything, but it's good background. So that's section 1.3. Some of this stuff is stuff that kind of blows your mind the first time you see it, but I will also say we're not going to use a lot of this stuff in section 1.3 too often, but it is absolutely essential background for anybody who wants to be a mathematician. This is stuff that all mathematicians know and think is pretty cool, and stuff that you want to get your mind wrapped around now, because it's not the sort of thing you want to be wrestling with 10 years down the line. So that's section 1.3, and I'll see you again in the second half of this weekend's reading, sections 2.1 and 2.2 in the next video.